So last time we spent the whole lecture talking about the simplex algorithm for linear programming, right? And the core idea of the simplex algorithm was to have this notion of a basis B, a certain collection of columns. Oh, sorry, remember we're using standard form where we're trying to minimize Cx, Ax equals B, x greater than or equal to 0. And after we make A have full row rank, we get linearly independent constraints. We then talk about a basis B of columns of A and corresponding basic variables, xi for I in the basis, and the other non-basic variables and our idea was that we sort of argued that every basic feasible solution in the polytope corresponded to a basis, right? In the sense that all the non-basic, at this basis that corresponds to a particular basic feasible solution, all the non-basic variables are 0, right? It's only the basic variables that are allowed to be slack. And so we then argued that just knowing the basis actually lets you reconstruct the particular vertex that you're at because you know that all of the non-basic variables are 0. And so you can solve this simpler linear system that identifies the basic feasible solution corresponding to the particular basis that you've chosen, right? And then we talked about this idea of doing a pivot, right? We used the basis to define certain, to sort of focus our attention on being allowed to change the non-basic variables, right? So we defined these reduced costs C tilde n on the non-basic variables and we said that using these reduced costs, we could express the value of our objective function just in terms of some constant AP inverse times B plus a function of something that's linear in the reduced costs, right? And so we were then able to say, well, if all of the reduced costs are non-negative, then any increase in any of the non-basic variables, making any of them non-zero, is just going to make your objective function worse. So that would tell you you're at optimum. On the other hand, if any non-basic variable is negative, then you have a potential to improve the value of your objective function by increasing the corresponding non-basic variable from 0. Because we have a representation of the basic variables as a function of the non-basic variables, we can make that change to the non-basic variables and get new values for the basic variables that correspond to that change. And that gives us a new point with an improved optimum if we've managed to increase one of the, or with an improved objective, if we've managed to increase one of the xn's. And so that's that's called a pivot. We increase some xn or some xi in the non-basic variables with c tilde I less than 0 to decrease the objective until some xj, where j is in the basis, becomes 0, right? And that can only improve the objective function or can't make it worse because our objective is expressed only in terms of the non-basic variables and we're increasing something that has a negative coefficient. And so that's what's called a pivot. And of course, once that basic variable becomes 0, we move the basic variable out of the basis and we take this now non-zero variable into the basis. And that gives us a better vertex. And that works great unless right away, as soon as we already have a 0 basic variable that tries to become negative when we increase the non-basic variable. In that case, we don't get any improvement at all. But in that case, we can still move that basic variable out of the basis because its value is already 0. And so we can perform a pivot that doesn't improve the objective at all, right? But we're still changing the basis. And so we keep making these changes to the basis until we get stuck, right? Until there's no way to improve the basis. And we talked about how we want a non-cycling pivot to guarantee that we don't keep changing the basis back to what it was before. And we argued that such a non-cycling, that there exist pivot rules that are non-cycling pivot rules that guarantee that you won't visit a vertex more than once, or you won't visit a particular basis more than once. Actually, it's not, I'm drawing that distinction because in fact, although I didn't mention this last time, if you think about it, when you do have a pivot step that does not improve the objective function, right? You bring in a different constraint, but you're not actually able to get any change in the objective. One of the ways that can happen is if you have more than n constraints intersecting at a single point, right? Which is what's called a degenerate polytope, right? N linearly independent constraints are enough to define a particular point, but you could have other constraints that are dependent on those that also run through them. So that's one way to get pivots that don't make progress. Another way is to move along an edge that actually has length but is sort of perpendicular to the objective function. So you get two different vertices that both have the same value. Okay. But we went through all of that last time, talked about the fact that simplex is not actually a polynomial time algorithm because there are these pathological cases where it will visit all of the vertices of the polytope, of which there can be exponentially many, but that it's fantastic in practice in many, many cases. But there was one more thing that I wanted to say about simplex before we leave it behind, and that's talk about duality a little bit, okay? We defined these reduced costs, and we said that at optimum, that vector of reduced costs is non-negative, right? So there's no place where we can improve the objective. So let us define at that point a value y to be equal to CB times AB inverse, okay? Remember, AB is a square matrix that takes the column vectors corresponding to the basic variables, right? And we argued that it's going to be full rank, and so it's going to be invertible. Okay, and so we then multiply that by the vector CB. So of course that means that CB is equal to y times AB, just by definition, okay? that means by the definition of the reduced costs that Cn tilde is equal to Cn minus Cb AB inverse An, which is just equal to Cn minus Yan by the definition of Y. Okay? We just said that the reduced costs are all non-negative. Looked over here, what that means is that Cn is greater than or equal to Y times An, right? Just doing some regular algebra here. Okay, so what do we have here? We have that C sub b, the coefficients of C that correspond to the basis satisfy CB equals YAB. On the other hand, the coefficients of the objective that correspond to the non-basic variables satisfy that Cn is greater than or equal to Yan. So if I combine these two things, right, that CB equals YAB and Cn is greater than or equal to Yan, right? If I put them together, what that tells me is that C is greater than or equal to YA, or just to ram the point home, that YA is less than or equal to C, right? It just follows from this Y that I've defined, it follows that YA is less than or equal to C. Okay? Now, what does it mean for YA less than or equal to C? Given that I've sort of set this up by saying we're talking about dualities. What does it mean that YA is less than or equal to C? Yes?
It's feasible for the dual.
Right. Y is feasible for the dual. Okay. All right. We have a dual feasible solution. Let's figure out its objective value. Right? In the dual, what is the value of the objective as a formula? Yeah?
YB.
It's YB, right? So the objective is YB. Okay, let's plug in Y, right? This is CB times AB inverse times B, right? Now, I actually did succeed in getting everything I needed onto the previous board in background. We have here CB AB inverse times B. Let's rewrite that. What is AB inverse times B? Yeah, it's XB, right? Okay. So CBXB is YB. But this isn't exactly CX, right? We also have CNXN. But what is CNXN? Yeah? 0. Why? Those were the non-basic variables, right? So if we put these two things together, right, that tells us that put these two things together, CX is equal to CBXB plus CNXN, just breaking apart the dot product, which is equal to CBXB. So what this tells us is that in fact, YB is equal to CX. What does that mean? Right? Again, we've started this process when we're at the optimum of the primal, right? We're at CX. See, we've said CX is optimum. So what does it mean when CX equals YB? Yeah? It means Y is dual optimal. So, even though we didn't do it, even though we weren't looking for it explicitly, right, the termination condition of the simplex algorithm actually gives us an optimum to the dual linear program, as well as an optimum to the primal linear program. Okay? So this is kind of like backwards from what we were saying. Before we said that solving the dual is just like solving the primal, right? It has the same value. The simplex algorithm makes that explicit. It sort of says that, well, of course they have the same value, because when I find one, I also find the other. Okay? Simplex, what I should say is, when simplex terminates, it has x and y such that cx equals by, and both are feasible. So of course they're both optimal, right? What's interesting about this is that it means that the simplex algorithm is actually a way to prove strong duality, okay? So proving that simplex terminates proves strong duality. Make sense? And what did we have to do in order to prove that simplex terminates? We had to prove that there is a non-pivoting pivot rule. A non-cycling pivot rule, right? If there is a non-cycling pivot rule, it guarantees that you never visit a basis more than once. There's a finite number of bases, therefore the simplex algorithm terminates, right? Unless, yeah. And so this is this is an algorithmic method for proving strong duality. Okay, you say here's an algorithm, and from the way this algorithm works, I can derive strong duality. Now, if I were going to do that, I would have to be much more careful about proving the existence of a non-cycling pivot rule. I kind of waved my hands about it. But if you do it really rigorously, then you get a rigorous proof of strong duality. Okay? I prefer the physics proof that we did because I think it provides more intuition. But some people like algorithms, so this is another way to get it. Any questions about that? No? Okay, so, well, simplex dominated for decades, but it left behind, or it begged this one really lingering question, which was, can linear programming be solved in polynomial time? Right? And so this was answered in the affirmative in the 1970s by Katchen. Who showed that indeed LP could be solved in polynomial time by giving a polynomial time algorithm for linear programming. And so that's what we're going to talk about next. Okay. I'm going to give you sort of the general structure here, but I'm not going to go into full formal stuff because really formalizing the ellipsoid algorithm, it takes a book. There's this very famous book by Gretschel, Lovaas, and Schrijver, which it's a gorgeous book, very important, and these three people are some of the deepest thinkers in combinatorial optimization. I know a very famous professor of optimization, who says that he reads one page of this every night before bedtime. Okay, because that's sort of all his mind can absorb in one sitting. It's a very deep book. It kind of gets to the ellipsoid algorithm almost as a side note. It actually, a lot of it is about lattices, which just is another way of talking about the fact that what we understood from linear programming, that things happen in fixed precision, right? So we articulate linear programming as if it's about the real numbers, but what we said was that actually all of the vertices are at things that have a polynomial number of bits in them. And so if you think about all the numbers that can be represented with a polynomial number of bits, well, you can cast out the denominators and be left with integers, right? And so really, the way we algorithmically deal with linear programming is as if we're working with integers, right? And so the points that are interesting to you in solving linear programming are the integer points of the high-dimensional space. And these sort of regularly spaced points form what's called a lattice. Okay, and so the book is a lot about lattices and also about combinatorial optimization. So if you want to go deep, you can take a look at that book. I'm only going to take you on a sort of shallow journey. So the idea behind the ellipsoid algorithm is to actually, it's a simpler idea than simplex, right? Simplex is thinking a lot about geometry and linear algebra and kind of moving your point carefully along edges of the polytope and so forth. The simplex algorithm goes to a simpler approach of trying to just guess answers and sort of update when you're wrong. Okay, so we've all seen this in the one-dimensional world, right? If I say I'm thinking of a number, what do? Well, you guess a number, right? And I tell you if it's higher or lower. And based on what I tell you, you update your guess, right? And if you think about it, I have to give you a little bit more information than just telling you I'm thinking of a number, right? What else do I have to tell you if you're going to have some hope of getting to the number I'm thinking about? Yes?
The range of the number.
I need to give you some sort of range, right? Otherwise, you keep guessing and I say no higher, and you guess again and say no higher, and I just keep on saying higher, 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 right? But if I put a limit if I put an upper and lower bound, then you can sort of home in on the number I'm thinking of through a kind of binary search process, okay? And the ellipsoid algorithm basically generalizes this to higher dimensions. And one example, one nice sort of poetic version of this, I don't know how many of you have seen the treatise on how mathematicians hunt lions in the desert. Who's seen this? Nobody? Oh, that's sad. Okay, so after class, go Google mathematicians lion hunting in the desert, and it basically has this long list of techniques, right? How do topologists hunt lions in the desert? How do functional analysts hunt lions in the desert? How do combinatorialists hunt lions in the desert? So on and so forth. And the particular method that we're going to be talking about is called the Bolzano-Weierstrass lion hunting method. Where you basically say, okay, here's the desert, I'm hunting for a lion, and I just build a big fence across the desert, and I say, well, the lion's either on the left side or the right side of the fence. So if I sort of can posit that they're on the right side of the fence, I can just build another fence across the desert and again subdivide the area, and I can keep on building these fences and subdividing the area until the lion is in such a small space that I can see them, and I've caught my lion, okay? And that's essentially what the ellipsoid algorithm is doing, is building these fences and homing in on what you're looking for. And it's easiest to talk about it as finding a feasible point. We're not going to worry about the optimization side until the end, okay? So essentially, you can think of it as me asking questions, is the feasible point here? And somebody tells me, nope, it's higher than here or lower than here. but we do need to generalize the notion of higher and lower to a higher dimensional space, right? So the ellipsoid algorithm begins by query a candidate feasible point. And if it is feasible, you're done, okay? If it's not feasible, however, then you need to be told what makes it not feasible in a way that will guide you towards a feasible point. So if I have a point that's not feasible, what's the obvious way to demonstrate to me that it's not feasible? Yeah? Exactly. You receive in response either, yes, it's feasible, or what is called a separating hyperplane. Okay? Which is to say that your point is on one side, and all the feasible points, say the query is on one side, and all the feasible points are on the other side. Okay, and that you can now test, right, that your point is not feasible. And so now you can go look on the other side. Okay, that's the general idea, but it's not going to work if we just do that, right? Again, we need to assume that there's some initial bounds, which can be expressed as a box, right? The point, if there is a feasible point, there's one in the box, right? But now we start making queries, right? It might be natural for me to ask about the center of the box, okay? And somebody says, no, right? Here is a violated constraint, or here's a separating hyperplane. Right? If we're doing linear programming, then an obvious place to find that separating hyperplane is to look at the constraints, right? A violated constraint is a separating hyperplane. Ellipsoid is more general. You might get a separating hyperplane that's not actually one of the constraints, but certainly a violated constraint is one way to give a separating hyperplane, okay? And actually, I can assume without loss of generality that the hyperplane is given with going through my query point, right? You can just move it away from the feasible set until it hits the query point, okay? So that's great. Now I know that, the feasible region, that I can sort of rule out this entire infeasible region that's on the wrong side of the separating hyperplane. So now I can make another query, right? And again, I'll get a separating hyperplane, right? And so each time I make a query, I get another separating hyperplane. And that homes me in to a smaller region of the space where the feasible points are, okay? So that seems very appealing until you ask yourself, what do I need to do in order to make my next query? Well, in order to make my next query, I need to pick a point that is still in the acceptable region, right? That sort of obeys all of the constraints that have been shown to me so far, right? Now, what is the problem of picking a point that obeys all the constraints I've been shown so far? What kind of problem is that? Yeah? That is the problem of finding a feasible point in a polytope, which is exactly what we're trying to solve, right? So that didn't get us anywhere. So the clever insight of the ellipsoid algorithm is to work with something that's not polytopes, okay? So having this sequence of shrinking polytopes means that you have to pick a point in a polytope in order to make your query. The ellipsoid algorithm uses something different than polytopes, where it's easy at each step to pick a point inside your object. What objects do you suppose the ellipsoid algorithm uses where it's easy to pick the next query point? Any guesses? Ellipsoids, okay? So, shrinking polytopes makes it hard to pick the next query point. So instead, because it's just doing the LP feasibility problem. So instead, what the ellipsoid algorithm does is shrink ellipsoids. Okay. So now we can talk about how the ellipsoid algorithm is actually framed. Okay. So what you do is you're given an ellipsoid that contains the feasible region. Okay. Now, what's an ellipsoid? An ellipsoid is just the generalization of an ellipse. Okay, and we'll do the math for it in a second. But basically, you know, it's a sphere that's been stretched in different amounts in different directions. Okay, so you're given an ellipsoid that contains the feasible region. You query: is the center of this ellipsoid feasible? Okay, so here is my ellipsoid. Right? I query if the center of the ellipsoid is feasible. Okay. If yes, you're done. Otherwise, we're going to find a smaller ellipsoid. You're given a separating hyperplane. That goes through the center. So here's my separating hyperplane through the center. And we then draw a smaller ellipsoid that still contains the feasible region. And so this is our notion of progress, is that each query, again, with binary search, each query shrinks the interval. With the ellipsoid algorithm, each query shrinks the ellipsoid. Okay? But we do need to shrink in a way that we continue to contain the feasible region. Right? How can we guarantee, we don't know what the feasible region is, how do we guarantee that we still contain it? Well, we draw a smaller ellipsoid that contains the entire half that hasn't been excluded. By the separating hyperplane. So if we're able to contain the entire half ellipsoid, then certainly we're containing the entire feasible set, because the assumption is that the feasible set was inside of the previous ellipsoid. Right? So how might we do that? Well, again, I'll fill in the math in just a minute, but roughly speaking, you know, if this has been excluded, we need an ellipsoid that's big enough to cover the whole vertical line and also this whole side, but we can shrink a lot in this direction because we don't need any of this half. So the new ellipsoid is going to be shaped something like this. Oops. Sorry, I am not a great artist. Okay, so it gets a little bit taller, but much skinnier. And we're going to argue that that combination of getting a little bit taller and much skinnier makes the ellipsoid have less volume. Okay? So is that general plan clear? Okay, good. So, I mean, as with simplex, we're focusing on the improvement step. We'll need to go back and talk about the sort of starting conditions and ending conditions and stuff, but let's for now focus on the improvement step. Okay. So let me fill in some math. So I'm going to define an ellipsoid E, and I can do that using a matrix and a center point for the ellipsoid. It's just equal to the set of points x such that x minus z transpose times d inverse times x minus z is less than or equal to 1. Okay. Where D is a positive semi-definite matrix, which just means that it has a square root for some invertible matrix B. Okay. You know, with our knowledge of matrices as sort of linear transformations, right? This is basically saying that the ellipsoid is a linear transformation of the sphere, right? You can stretch it, you can shear it, and so forth, but you're starting with a sphere and then you're applying a linear transformation, okay? So in particular, E, if you use the identity matrix, and Z is the sphere centered at Z, and E of dz is a map of the unit sphere via the affine transform that takes point x to the point bx plus z. Okay, and that's why we want D to have this nice square root. Okay? So it's a linear transformation of the sphere. And we're going to start with a big ellipsoid that encompasses the entire feasible region. And we are going to perform these improvement steps until the ellipsoid is too small to encompass the feasible region. Okay? And if we get to a point where the ellipsoid is too small to encompass the feasible region, we're violating the invariance of the ellipsoid algorithm, which means that sometime before then we must have found a feasible point, because that's the only other way for us to stop. Okay? So let's talk about the math behind shrinking the ellipse. So you know, I've got my current ellipsoid, my D and my Z. I'm just going to assume that it's a sphere centered at 0, right? If I have a different ellipsoid, I can apply a linear transformation to turn it into the sphere centered at 0, right? Just inverting this one, right? Now I can talk about my separating hyperplane there. I can create my smaller ellipsoid there, and then I can reverse that linear transformation to get back to the original coordinate system, and my new ellipsoid will be transformed into a new ellipsoid in the original coordinate system. Okay? Right? Because what we can do is we can reverse the affine transformation that represents the current ellipsoid, right? We can separate and find the new ellipse in the easy coordinates, and then we can retransform to the original coordinates. what's important is that any affine transformation has an inherent volume transformation, right? So a given affine transformation will change the volume of any shape by the same amount, okay? And so what that means is that running the affine transformation forward and back will preserve the ratios of the volumes of two different objects, okay? So if we make an ellipsoid whose volume is less in the easy coordinate system by a certain ratio, then it will also be less by that same ratio in the new coordinate system, okay? So this lets me do everything in the easy coordinate system. So let's think about that easy coordinate system, right? It's, I mean, I've got the picture right here, but let me draw it a little more carefully now. So there's our sphere. Here is our center. Our query point is starting at the origin. If we're going to make an ellipsoid that looks like this, God, I'm so bad at drawing. This is why I never went into computational geometry, right? I can't possibly do that if I'm such a terrible drawer. So this ellipse, you know, in all of the other high dimensions, everything is symmetric. I'm just sort of specializing out the dimension in which we're going to squash the ellipse. It's going to grow by the same amount in all of the other directions. So just pictorially, you can see that what I'm going to be doing is shifting the center of the ellipse a little bit rightwards by some distance, okay? Let's call that distance, well, what do I want to call it? Yeah, let's call this epsilon, distance that I need to move the center over, okay? Because the new ellipse is centered somewhere to the right of the old one, okay? So we're going to center this ellipse at epsilon, but we're going to leave all of the other coordinates 0, okay? And now let's ask, what are the requirements that this new ellipsoid has to satisfy? Okay. So remember, the formula says that sort of the scaled distances all need to be less than or equal to 1. So the new D matrix is going to be a diagonal matrix because I'm using sort of an axis parallel ellipsoid. And so the formulas that are going to be required are first that, let's see which one. Yeah, the general formula is going to be that d1 inverse times x1 minus epsilon squared plus the sum over I greater than 1 of di inverse times xi squared. That all has to be less than or equal to 1, right? That's the formula for the ellipsoid in the special case of a diagonal matrix. Okay? So where is that constraint going to be tightest? I claim that it's going to be tightest sort of at the far end of the ellipsoid and at the places where the ellipsoid runs into the axis. Okay, again, you can just sort of see that pictorially, right? What stops me from making this ellipsoid any smaller is that I can't shrink it in this direction anymore because I would lose this end of the original sphere, and I can't shrink it in this direction anymore because this is the point that I would lose if I shrank it in this direction. Okay, so it's going to pass through. It's going to pass through this point, and it's going to pass through this point. I'm going to have equality here. So let me write out those constraints. The first one, at the point 1, 0, and so on, tells us that d1 inverse times x minus epsilon squared has to be equal to 1, right? In other words, d1 is just equal to 1 minus epsilon squared. Okay. Another thing just to think about with this diagonal matrix with these di's, right? These di's are basically telling you how far you scale each of the axes, right? We're not doing any rotation of the ellipse or anything like that. We're just stretching or shrinking along the different axes, right? And so what this is telling me is that I can shrink along the x-axis, okay? I can make d1 smaller. Now let's look at the constraint at 0, 1, 0, and so forth. Okay? So here we have a constraint on D1. What is the constraint here? This is saying, here what we're going to say is that epsilon squared over 1 minus epsilon squared, right? This is x1 minus 0, right? Because our center, right? We're now looking at basically at this distance, right? So by Pythagoras, we've got an epsilon squared over 1 minus epsilon squared. That's from D1 plus D2 inverse has to be equal to 1. Right? Everybody buys this as the proper distance constraint, or the proper scale distance constraint for this point? I can't tell if everybody just completely gets it or is lost. Anybody want to tell me? Keep it a secret. Yeah? Sorry?
Makes sense.
Makes sense? Okay, good. So if I solve for this, I find out that D2 inverse is equal to 1 minus epsilon squared divided by 1 minus epsilon all squared, which is about 1 minus epsilon squared, right? This is about 1, okay? Now, notice these are not entirely consistent, right? This is saying that D1 got smaller than 1. This is saying that D2 inverse got smaller than 1, so actually D2 is about 1 over 1 minus epsilon squared, or about 1 plus epsilon squared. And this is also true for all the other Ds, right? D3, D4, and so on and so forth. So what this tells us is that if we shrink the sphere along the x-axis by a 1 minus epsilon all squared amount, but we grow the sphere in every other direction by a 1 plus epsilon squared amount, we get this slightly taller but thinner ellipsoid, which contains the entire right half of the sphere. Everybody agrees with that? Now, the critical question is, what is the volume of this new ellipsoid? Well, we're doing a series of stretches and squashes, and they each cause a volume change that multiplies the previous volume changes, right? So the change in volume, the new volume, is just equal to the product of the di's. Right? We shrink in direction 1 by 1 minus epsilon all squared. That decreases the volume by 1 minus epsilon all squared. We grow in the other directions. That grows the volume by their corresponding amounts. So this is equal to Sorry, I just think I may have lost a square here. Hang on a second. Nope. Okay. I'll fix that later. So this is roughly. Oh, I see what happened. Okay. So this is roughly 1 minus epsilon all squared, right? Divided by 1 minus epsilon squared to the nth power. Okay. Oh, I see what the problem is. These di's, the volumes are actually changed by the b, by the square root of the di's, right? So I need to put a square root around here. Okay. All right. And so that is equal to 1 minus epsilon divided by 1 minus epsilon squared all to the n over 2 power. Okay. So did the volume grow or did it shrink? Well, it turns out that depends on epsilon. Okay. So if we define epsilon to be equal to, say, 1 over n, okay, then what we get is 1 minus 1 over n divide, let me make it 1 over 2n. What we get is 1 minus 1 over 2n times 1 minus 1 over 4n squared, all to the n over 2 power, right? But we can approximate this, right, as sort of in terms of the initial term, right? This is about 1 minus n over 2 times 1 over 4n squared, right? Which is 1 minus 1 over 8n, right? So we have 1 minus half n divided by 1 minus 1 over 8th n, and so this is equal to 1 minus order of 1 over n. So the volume does shrink. Okay. If you use a big epsilon, then the denominator gets small, right? Gets smaller than the numerator. But if you use a very small epsilon, the fact that we're squaring inside the parentheses makes this term much closer to 1 than this term. Okay? And so we get a kind of 1 over n progress in shrinking we shrink the volume by a 1 over n factor. Okay? Any questions? Okay. So that's the whole story of the single step, of the improvement step. Okay? Notice that n steps, or order n steps, shrink the volume by 1 minus order 1 over n to the order n power. So if you set your constants properly, order n steps will shrink the volume by a constant factor. Okay. So now we're done with the improvement step. We need to now plug this into the whole algorithm, which talks about starting and finishing. But I'll do that after we break. Are there any final questions about this improvement step? No? Okay. Yes?
The motivation behind taking beta to be, or epsilon to be 1 over 2n.
The motivation is, if you think about it, if you make epsilon too large, okay, then the 1 minus epsilon squared term in the denominator, right? Basically, this Taylor approximation stops being valid, and the numerator gets smaller than the denominator. Sorry, the denominator gets smaller than the numerator. If the denominator is smaller than the numerator, then the ellipsoid is actually getting bigger, right? So the point is, we can't make epsilon really big, but as long as we make epsilon small enough, the ellipsoid shrinks. And that's what we want it to do. So what this analysis did was figure out how big is it safe to make epsilon, right? The point is that, right, if you make epsilon really small, right, then your volume improvement is only 1 minus epsilon. So if your epsilon is really tiny, then you don't get enough volume improvement, right? So there's this, we're basically finding this nice middle ground where the volume decreases by a 1 over n factor, which is big, which is enough for our purposes. Okay, good question. Any others? Okay, let's take our break. Yeah, there's a lot of math. You should work it off, right? Get some. Everybody's just sitting stunned by the amazingness of the ellipsoid algorithm. Kind of stand up, do something, you know, move around a little bit. All right, let's resume. So we have this local step, and I think you all agree that that a single step can be executed in polynomial time, right? You need to perform a certain linear transformation, and I mean, you're doing a bunch of algebra, but nothing complicated. And that gives you the next ellipsoid. So we have this polynomial time algorithm that decreases the ellipsoid volume. So in order to define the entire algorithm, we need to think about the starting and ending of that algorithm. And in particular, the overall runtime derives from the ratio of the starting volume to the ending volume. Right? If the ending volume is only half the is half the starting volume, well then we'll stop. Then we'll finish in n steps, right? More generally, it's n times, or order n times the log of the ratio between the starting volume and the ending volume, right? Since we're geometrically decreasing the volume, that's where the log comes from. So we just need to understand how small, right? So obviously we want to make the starting volume small, and we want to make the ending volume, or we want to prove that the starting volume can be small, and we also want to argue that the ending volume won't be too small. So let's do the starting volume first. That's an easier story. What's the invariant we require? We require that the feasible region, if it exists, has to be inside of our ellipsoid. So in order to kick off the algorithm, we need to define an ellipsoid that is guaranteed to contain the feasible point, the feasible region. That is, it just has to be guaranteed to contain the entire polytope. Okay. How can we do that? Yes? That is true. It is sufficient. You're absolutely right. Actually, no, we have to be careful. If it only intersects the polytope, then it might intersect it at an incredibly tiny volume. And so the part of it, yeah, so sorry. This highlights that I actually have to talk about start and end at the same time. Okay. What we're eventually going to show about the end is that the polytope itself can't have a small volume. Okay? And that's going to let us stop the algorithm before the ellipsoid gets too small. But if we only worry about intersecting the polytope, then that intersection might have a tiny volume. And so we might have to wait for the ellipsoid to get even smaller than that tiny volume. Okay, so we are going to want to maintain the invariant that the entire polytope is inside of the ellipsoid. Okay, so how can we do that? Like, how do we know there's any ellipsoid that contains the entire polytope? Let's assume the polytope is bounded, right? If it's not bounded, then there's no, right? But you can always make the polytope bounded, let's start by assuming that the polytope is bounded, and we'll fix it later, okay? So assuming the polytope is bounded, can we say anything about the limits of how big it can be so that we can fit an ellipsoid around it? Yes? Good. So we know that the sort of extreme points of the polytope, definition, right, are the vertices. They're the farthest out in any direction. Now, what do we know about the vertices? Right? So it is sufficient to contain all the vertices. Right? Because if you contain all the vertices, every other point is a convex combination of the vertices, so it's inside of the ellipsoid as well. So how big do we have to make the ellipsoid so that it contains every vertex? Well, that comes down to a question of how big can the vertices be? And what do we know about that? Can the vertices be infinitely large numbers? Yeah?
I guess we showed that we could represent them with a polynomial space.
Exactly. Vertices have poly of mn bits, which implies that they have at most 2 to the poly of mn magnitude, right, or value. Okay? So every coordinate of a vertex is a number that is smaller than 2 to the poly of mn. So if we just make the radius greater than n times 2 to the poly of mn, it will contain all the vertices, right? And if the radius is n times 2 to the poly of mn, then the volume becomes n times 2 to the poly of mn raised to the nth power times some constant, right? Which is still 2 to the order of a polynomial, or sorry, 2 to a different power, to do a different poly of m and n. Okay? So the initial volume is at most exponential. Okay? Why is that good? Well, when we take the log of that in our runtime, right, that log of an exponential turns back into a polynomial in m and n. Okay? So at least in terms of starting point, we're okay. We have something that looks like it's going to give us a polynomial. But we also have to worry about the ending. Okay? Oh, actually, let me deal with this issue of what if the polytope is not bounded. Okay? If the polytope is not bounded, then you might think you have a problem, right? I mean, you can't make a sphere that contains the whole polytope. But the problem is, in a sense, only you can add, if the polytope is not bounded, remember, we're just looking for a feasible point. So you can just put a big box around the polytope. You just add some constraints that turn it into a bounded polytope, right? If it was feasible before, then it's still feasible after you add some very large bounding constraints, and then the previous argument applies. What about the ending? Okay. Question is, how small can the ellipsoid be? Well, we stop when the volume of the ellipsoid is less than the volume of the polytope, right? So if we can just lower bound the volume of the polytope, we're fine. That becomes a bound on the volume of the ellipsoid, of the stopping volume of the ellipsoid. Now we immediately have to worry about something. Okay, you can have polytopes that are not full dimensional, right? If I have an ax equals b constraint, that makes the polytope be not full dimensional. What's the volume of that polytope? Yeah? Is 0. That's not very useful. Okay? So what I'm going to do is, without loss of generality, I'm going to basically eliminate equality constraints. I'm going to, shoot, I've lost my words. I'm going to simplify, what's the word I'm looking for? What do you call it when you have a problem with many variables and use an equality constraint to get rid of one of the variables? Why am I blanking on this? Right? Use the equality constraints to eliminate redundant variables until there are none. Okay? So there are no more equality constraints. So now you only have inequality constraints. And essentially at this point, your problem is a full dimensional. It's sort of the picture from the canonical form, right? The inequality constraints can always be used. You can always turn it into a full dimensional problem. It's a little more complicated than that because sometimes the equality constraints could be implicit, but, but you can do it just using just solving linear systems. Okay? It turns out, and this is where I'm sort of abandoning formalism, right? There is a theorem that a full dimensional polytope, let's say it a different way. This polytope contains, because it's full dimensional, n plus 1 affinely independent vertices of the polytope. Okay, so what this is basically saying in 2 dimensions, you have 3 vertices that are not affine combination of each other. Okay, and this defines a very simple polytope, which is the convex hull of n plus 1 vertices of the original polytope. Okay, that convex hull is what's called is a variation on what we can call on what's called a simplex. And there's a theorem that its volume has a number of bits, which is polynomial in n and the bits of the vertices. Okay, so this is sort of a continuation of what we saw about vertices of a polytope, right? We said that the vertices of the polytope, the number of bits in those vertices is polynomial in the number of bits in the defining constraints in the dimension of the problem. Similarly, you can prove that the number of bits you need to represent the volume is polynomial in the number of bits of the vertices that define the polytope. And so it's of the same order. Okay, and that means that the value of the volume of this min volume is at least 2 to the power of minus some polynomial in n. Okay. And so again, when we apply a log, right, we basically, because the starting volume is 2 to a polynomial number of steps will shrink the volume to a constant. Right? Once the volume is a constant, because the ending volume is 2 to the minus a polynomial number of steps will shrink the volume of the ellipsoid below this volume. So all in all, you just need a polynomial number of steps to go from the biggest possible volume that you need to worry about to the smallest volume that you need to worry about. Okay, and this arrives us at our conclusion that the ellipsoid algorithm takes a number of steps, which is polynomial in the number of constraints and the dimension and the bits of the constraints steps, i.e., it is a weakly polynomial algorithm for linear programming. Okay? And again, the details of all of this, if you want to spend the time, can be found in Grotchelova-Schreiber. Okay? Now, this begs another question, right? Is there a strongly polynomial linear programming algorithm? The answer is nobody knows. Okay, that's still a very important open question. We do have polynomial time algorithms with really great runtimes for fixed dimension, but for general dimension, the best that we can say is that we have a weakly polynomial algorithm. Now, I want to finish up with a couple of interesting observations regarding ellipsoid. The first is that so it's theoretically great. not a very good idea in practice. The running time, once you unpack all of this, is like n to the sixth or something. Okay, so you don't want to use it for real. But for theoreticians, it's actually even more amazing than just being a polynomial time algorithm, because like what did we need in order to run the ellipsoid algorithm? Okay, we needed to be told when we asked about a query point, we needed to be told a separating hyperplane. Okay, now if you think about it, that means we didn't need to know the constraints of the linear programming problem. We just needed somebody to tell us one of them at a time when we ask questions. Okay? And so in fact, the ellipsoid algorithm even if you have exponentially many constraints, or in fact, infinitely many constraints, as long as you have somebody to tell you one of them is that's violated when you have a particular point, right? All you need is a so-called separation oracle. That gives a violated constraint. For any infeasible point. Okay? And this turns out to be incredibly useful in theory, in algorithms. Okay? There are some wonderful results that use the ellipsoid algorithm to solve problems where you have way too many constraints to actually write them down. You have implicit representations of the constraints, and it's just enough to find one of them that's violated when you're given a query. And the ellipsoid algorithm is still going to run in polynomial time. Right? So really the polynomial depends only on the dimension and doesn't care how many constraints there are. Yes? Yes, there are amazing generalizations of the ellipsoid algorithm. The technique that we've talked about here, this shrinking of ellipsoids, can actually be applied to a more broad class of problems known as convex optimization, right? Where you're trying to optimize convex functions, not just linear functions, under various kinds of convex constraints. Okay? Yes?
Even if we have exponentially like many constraints, we still have to show that the vertices can be stored in our coordinates.
Yes, it gets tricky, right? So like if you really think about it, if you have infinitely many constraints, right, then you can define a sphere, right? It's just all the hyperplanes at distance 1 from the origin, right? That defines a sphere, and it has vertices that are like all of the points on the sphere. A lot of them have irrational vertices. So you have to be careful when you use this technique. You sometimes have to go back to the beginning and argue that, yeah, we really still do have polynomial representation of the polynomial size representation of the solutions. Okay, so you have to be careful, but it works. Okay, yes?
How much work does the oracle have to do to give you the separating?
Well, that depends on the problem. So I think I'll put one of these onto your homework, which sort of gives you an example of, come up with a separation oracle for this problem, and then just say, okay, it's solved because the ellipsoid algorithm can do the rest. So, and that's sort of the approach, right? If you have a new problem, if you're able to just come up with a separation oracle, that's all you have to do, because then you can hand it off to the ellipsoid algorithm. So you just need a way of showing that a point is infeasible, which is way easier, right? It reduces the problem of finding a feasible point to the problem of, in polynomial time, demonstrating that a point is infeasible, which is way, way easier. Okay? All right, so last words. This gives us a polynomial time algorithm, but it's not practical, right? In the 1980s, somebody named Karmakar developed a new class of algorithms called interior point algorithms. And I don't have time to tell you about these today. I'll do it later on. These initially got a tremendous amount of media buzz. They said, ooh, with interior point, you can solve the traveling salesman problem in polynomial time. which is false, of course. That's just the newspapers not understanding what's going on. But interior point are a different technique than the ellipsoid. It's basically solving linear programming by gradient descent. And it can be shown to run in polynomial time. And interior point, I mean, initially was impractical, but has now become very practical. And interior point algorithms are used everywhere to solve complex linear programs. They have guaranteed polynomial runtimes. And so they will win in cases where simplex does really, really badly. We don't yet understand like why sometimes interior point does better and sometimes simplex does better, and so you'll often try running both in the hopes that and expect that one of them will do well. But we do have now, through interior point, an algorithm with provable weekly polynomial running time that also is useful and very important in practice. Okay? But it represents the sort of continuous optimization that I, as an old-fashioned algorithm system, am allergic to. So I'll only give you I'll tell you about it for 10 minutes at some point, what the general idea is. But for details, you'll have to go take a real optimization class. All right? Thanks very much. You'll be back at lecture on Friday.